For today, I wanted to do a little video about 6.6 and reviewing some properties of logarithms and how to use them in a couple of examples of realistic exponential growth problems when you're trying to solve. So there are three, like we said, there are three basic properties of logarithms. The first one is the multiplication one, the product one. The log of u times v is equal to the log of u plus the log of v. So when you're multiplying two things and you're looking for their exponent of the product, if you multiply two things, you add their exponents to get the exponent of the product. So if you think about logarithms as exponents, to find the exponent for the product, you add the exponent of one plus the exponent of the other. Okay. And then there's the division one. If you have the log of the u divided by v, then you subtract the log of v, log of u minus log of v. And the third is this power one. The log of u to the n is equal to n times log of u. And we've talked about that as being, if you want to, how many periods does it take to get to a value of u to the n? Well, if it takes this many periods to get to a value of u, and you do that n times, you're going to multiply by u times u times u times u n times, or u to the n. So that would give you this. So each of those three you can think about in concrete context or just help to remember those properties. But they're also more clear if you use values for u and v that have easy logarithms, like nice powers of 10. So for instance, the log of this product, 10 cubed times 10 to the fourth, well, we know that's the log of 10 to the seventh. And so if we're trying to figure out the power for 10 to the seventh, well, that's the power for 10 to the third plus the power for 10 to the fourth. So we can get the product rule for logarithms in that case. What about if you want to think about the division one? So there's an interesting, those two properties are connected. So suppose we had this formula we have here and we want to subtract this to the other side. What happens then? We have the log of 10 cubed times 10 to the fourth minus the log of 10 to the fourth equals the log of 10 cubed. And so we could take this 10 to the third times 10 to the fourth and make it 10 to the seventh, right? And so essentially what we've done is reordered the equation we had before so that it's now a subtraction equation, and these two combine by our rule to give us log of 10 to the seventh over 10 to the fourth. And we know we subtract exponents, it was 10. So we know 10 to the seventh over 10 to the fourth, we subtract exponents, so we get 10 to the third. In that same way, we subtract logarithms, because logarithms really are the exponents that you get, the powers that you need. So we talked in class about how you can use these properties to solve exponential equations. And the most difficult case was if you have two different bases, base of 13 and base of 2, for instance, and you have various exponents. We're trying to find the value of x that makes those things equal. The trick that we talked about in class is if those bases happen to be nice, you can do other things, but in general, you change both bases to a nice base. In our case, we'll use base 10. And 13 is equal to the log, or 10 raised to the log of 13. Because log of 13 is defined to be the number that if you raise 10 to that number, you get 13. So that works. That's how it's set up. And similarly, log of 2 will give 10 to the log of 2 equals 2. So as we do that, we are able then to use our power rules for logarithms, or rules for exponents, and the exponent of 10, I can multiply those two exponents, and I get log of 13 times 5 minus x. And the exponent for 10 on the other side is log of 2 times 4 of x, 4 times x. So here I'm essentially just setting the two exponents equal, the two powers equal, and now I solve for x. So I distribute to get to this point. I distribute the 5 times log of 13 and the x times log of 13. And then what I want to do is move all the x's to the other side. So I add log of 13 times x on that side. And now I have an x in this term and an x in this term, so I can factor it out. X times what's left. And when we're all done with that, we can divide by this term, and we end up with what we've got. That's a lot of algebra real fast, but one of the nice things about these problems is that same process of algebra, multiplying, distributing things, moving all the terms with x's to one side, factoring the x out, and then dividing away, that process happens over and over again. So the numbers might look ugly and detailed, but the steps are similar every problem you go through. And we started off with bases of 13 and 2, so we're going to end up in our equation with logs of 13 and logs of 2. That's just how these work out. And I also said in class that we could kind of save a step by starting with this equation and taking the log of both sides, right? The log of 13 to the 5 minus x and the log of 2 to the 4x. And the nice thing about that is now you can use our rules for logarithms, and this 5 minus x comes out in front to be that 5 minus x. And the 4 times x comes out in front to be that 4 times x. And so we can get an equation here, which if you look back at the previous problem, that's exactly the equation we had right here. Well, no, one step before that. Right here, that's exactly the equation we had right there. So using that rule for logarithms, you can bring the exponent down in front. You kind of can skip this example of sneaking in that power of 10. Really, it's the same thing. It's just a little bit streamlined process for this. So I talked about in class one other example that I wanted to talk about here that has 2 cities. A small city that's growing 10,000 people. It starts at 10,000 people and it's growing 5% per year. And a large city that starts at 200,000 people and decreases by 10% each year. We talked about in class how you get this equation for that. The blue equation is the exponential growth for the small city. The orange equation is the exponential decay, because it's decreasing by multiplying by 90% each time. That's the large city. And how can you solve that? Well, one process you can do is to take the logarithm of both sides. That's right here. And by the formulas for logarithms, you can look at this box. It's a product, so I can take the log of 1,000 plus the log of the second part. But that second part, I can bring the exponent down in front to the t in front. I can do a similar thing on the right-hand side for this and break apart the log of that 2,000 times 0.90 to the t. And as we go through there, at this point we move all the t's to one side and factor out a t times log of 1.05 minus log of 0.90, and on the right-hand side we'll have this. When you divide, you get that equation for the end. And I'll just leave that sitting there. Again, that's a lot of algebra, but that same process works on each one of these problems. So if you take the logarithm of both sides and simplify them out by the rules, solve for t, you can get this. And it looks like an ugly equation, and it kind of is. It's not the prettiest, but it has some really nice properties. And I'll show you in just a second some things about those. But the numerator, you can look, the numerator kind of has in it the log of the large population and the log of the small population, and it has the growth rate of the small population and the growth rate of the large population. So all those numbers that we started off with are still sitting in that formula. If you want to plug them into your calculator and get decimals, you can do that, that's great. But I wanted to show you, we started this problem by taking the logarithm of both sides as a first step. which is great. Then we use algebra to solve for that. We could also start that same problem in a different way and simplify the problem, manipulate the problem before we take the logarithms. And I wanted to show you 2 steps to do that. The 2 steps are moving the parts with exponentials to one side, so that we would have these two together, divide by 0.90 to the t, divide that to the other side, and then divide the 10,000 to this side, and we end up with this. So we have all the t's on one side and all the numbers on the other side. And the nice thing is, since these in this example are both raised to the power t, I can combine them into a single fraction to the power t here. So all I've done is I've taken my 2 equations and done some manipulations before I take the logarithm of both sides. And now if I take the logarithm of both sides, I can do that, and this t that would have been up here comes down in front. And by the properties of logarithms at that point, and then I can solve nicely for t. I just divide by this thing that's in front of it. Whoops. This term that's in front of it. And again, you get an equation that has logs and the numbers, the numbers that have been following us around through this whole problem. But I wanted to point out how they're really very nicely tied together. So look at the, let me change colors here. Look at the numerator here. We've got the log of the big city over the small city. So that fraction is just how many times bigger the big city is compared to the small city. And it's the log of a fraction. So that's equivalent to the log of the big city minus the log of the small city. What about the denominators? The denominator is a log of a fraction. And the fraction is the growth factor of the small city over the growth factor of the big city. And so we're just comparing those, and that fraction in the other example becomes a log of 1 minus the log of the other. So these 2 expressions here in the green box and the pink box are really identical expressions. Just written in different ways because of properties of logarithms. And so I think that's kind of exciting how solving things in 2 different ways can get you the same answer, and you can see where the properties show that they're really equivalent.